This is Statistics 243 for Friday, October 31st at UC Berkeley. Okay, let's go ahead and get started. Okay, so we left off last time. We had talked our way most of the way through the LU decomposition and the relationship between the LU decomposition and Gaussian elimination. And I just wanted to put this up again as I was preparing problem set 7 some this morning. One of the problems is going to be on doing a bunch of stuff with the LU decomposition, so I just wanted to put this up again and to remind us that you can think of what we're doing is taking the A matrix, applying a bunch of these transformations that are summarized in these L1 up through Ln-1 matrices, and that produces the upper triangular U. So each one of these L matrices is going to zero out the values in one of the columns below the diagonal. And so the result of that is, okay, we have this, and what that says is we can then say that A is equal to the inverse of this times U. So the inverse of this is then therefore what we're calling the L matrix, and it does turn out to be lower triangular because all of these guys are lower triangular. And if you look at what the elements of these different L matrices are, L1, L2, up through Ln-1, it basically has these terms in them, which were the things that we came up with to try and make sure that we got the cancellations that we needed to zero out those values. So these pieces will be useful in at least one of the parts of one of the problems. So the other thing I wanted to say about the LU decomposition was to talk a little bit about implications of numerical accuracy on a computer for doing that, and these sorts of considerations hold for other factorizations as well. Were there any questions about this before I talk about that? Okay, so when we finished off last time, one of you, I think it might have been Lei, was asking about zeros, and I was doing a bad job of answering that question. So let me come back to that, because in part because I want to do a better job of answering, and in part because that actually leads where I want to go in terms of the numerical questions. So suppose that we have this. Suppose this is our A matrix, right? And what's going to happen the first time we try and zero out this value, or zero out any of these values in the A matrix, is we're going to be dividing by a 0 up here. And basically the algorithm is essentially going to stop at that point. Okay, so the question is, if we see something like this, what would we do that would avoid the problem of dividing by 0?
You can do a row swap.
Yeah, so I can just basically swap the rows. If the problem is that my algorithm says divide by the guy up here, well, it doesn't matter what order these are. I can just reorder the rows, and then once I get my answer, I'll just reorder my answer in the appropriate way so that everything works out. So basically, all I would need to do in this case would be to swap these two rows, and then all of a sudden I've got 0 divided by 3 instead of 3 divided by 0, and that would solve the problem in this case. So that's fine, and that's interesting and useful to know, but the real reason that is useful, the real reason this idea of swapping rows is useful is not because we're often going to have exact zeros. In fact, usually we won't, because we'll have done some computation, and it's going to be rare that we'll actually get an exact 0. Usually we'll have some floating point value that might be near 0, but isn't actually going to be exactly 0. But basically, if we then think about what's going to happen, is suppose we have an A11 that starts to get close to 0. So we know we can't accurately represent that number on a computer, and even more so, we know that if this number came from doing a bunch of other calculations, there's going to be even more inaccuracy having been introduced by the result of doing those calculations. So this is going to be inaccurate. If it's a small number, those inaccuracies are basically going to get blown up by the fact that it's in the denominator of doing this calculation. That inaccuracy is going to have larger ramifications because we're dividing by a number that's has a large relative inaccuracy. So the basic story of dealing with zeros carries over to the story of what happens if we try to divide by a small number. And so the idea is that this is called pivoting. These are called the pivot elements. And so basically what we do to avoid this instability of potentially dividing by a small number is when we're at this stage of the algorithm and we're dealing with the first column, we basically look through here and say, which of these values in the first column is the biggest one? That's the one I want to be dividing by, because that's the one that's going to have the smallest relative inaccuracy when I do the division. So basically, figure out which is the biggest one, maybe it's this one, and move that row up there. And then for all of the zeroing out that then is going to happen, I'm always going to be divided by that value, and I'm in pretty good shape. And now, okay, so then suppose I've zeroed out all of these. This is now a non-zero. Suppose I've zeroed out all of those elements in that first column that are below the diagonal. This is some non-zero value. These are now zero values. I'm now working with this n-1 by n-1 submatrix. I basically do the same thing. I look at all these values, I find the biggest one, and then I do a reordering of the rows to solve the same problem that I was addressing. So that's basically what there is to it. I have it here. It turns out you could also think about interchanging columns to make it even more robust. But it turns out that if you just do the row interchange, you do a pretty good job in terms of the numerical accuracy of doing this. And it also turns out that you can basically write what we're doing is that we're solving this problem. We're solving a problem where we take the A matrix, multiply it by some permutation matrix that does all this swapping, and then we're finding the LU of that. And we can always, anytime we want to find an answer in the correct order, we can always apply P transpose to whatever we get to basically do the reverse ordering. Okay, the other thing I wanted to do was just illustrate, just sort of with a numerical example, how this would work in just a very simple example. So suppose I had this set of equations. I just have a 2 by 2 matrix A, this guy 1, 1, and 1, and I have a two vector B, and I'm trying to find x1 and x2. If I actually just do this out and calculate it out by hand, this is the actual answer. But if I were trying to just do my straight LU decomposition without the pivoting, what would happen? Well, I'd keep the first row, and then the next row would be my A minus A21, which is a 1, over A11, which is this, multiplied by the first equation, plus a 1 multiplied by the second equation, and that gives me my new transformed second equation. So if we go ahead and work that out, that ends up being this equation. So now I have these two equations, and now I can do my backsolve operation to find x1 and x2. Okay, but now what I'm going to do is just play a little bit of a game here, which is suppose that I were working on a computer that was a really, really bad computer. And my really bad computer, which is from 1952 or something, or probably even longer ago than that, is only accurate to 3 digits. Okay, so I'm sort of trying to mimic the case of, in reality, what we're talking about is cases where we're thinking about 16 digits, but let's just simplify it and pretend we only have 3 digits of accuracy. Well, if that's the case, these guys, these two values here would become minus 10,000 x2 equals minus 10,000. And now if I solve for x2, I get that x2 is, sorry, if I could do arithmetic, I would get that x2 was 1 and not minus 1. Okay, and now if I plug x2 back into this equation, I would get that x1 is 0 and x2 is 1. So the solution on my very bad computer, which has reduced accuracy, is that I would have x equals 0 and 1 as my answer. And that's obviously very different than the actual true answer. So, yeah, if you right, I mean this would just be 1 times 10 to the minus 3. Right, so as long as we're representing it with floating point, with floating points, we were fine there. Okay. Okay, but if you do interchange these rows, and then just, I think I won't bother to do it here in detail, but if you did interchange these rows and still play the same game of pretending like we only had 3 digits of accuracy, you would end up getting that, you would end up finding that x1 equals 1 and x2 equals 1. So you wouldn't get these extra, you wouldn't get this accuracy, but you would get an answer that is more or less accurate. It was fairly accurate with respect to this, given the limitations that I've imposed, which is this pretending that I'm working with a very bad computer. So the idea of that example is just to say, well, okay, here's how we could see it in sort of a toy example. Now try and sort of think about generalizing that to, well, we have 16 digits of accuracy, that the same sorts of things would happen at sort of a different level of the calculation. Okay, other questions?
This is a notation, but in your pivot points for the general, the parentheses k minus 1.
Yeah.
What is that?
Yeah, so that goes back to last time. I may not have said very carefully what that was. Basically, okay, so this is just some value, and I'm just trying to say that it's standing in for that. But that basically, at any point when we're working with these sort of telescoping submatrices, I'm going to be somewhere down here, and I'm going to be dividing by, let's see, yeah, so I'm going to be dividing by this value. But this is going to be all of these values when I get to this stage, all of the values in here are going to be new values relative to A. They're going to all have been transformed in here. So that's why that's why the values in here would have been A something something, sort of the first iteration values. And this is the k minus 1th iteration because I'm now in the k minus 1th subblock. And that's the same thing that I'm doing up here with the 1 and the n minus 2 in the superscripts. Okay, other questions? Okay, so if you were to look up some help information on the solve function in R, you'd find out that in general, if you do a solve, you're going to end up using the solve.default specific method. And if you looked a little further, you'd find that calls a function called dgesv. That is a LAPACK routine, so this linear algebra package that R is calling. And if you did some searching for dgesv, you'd see, oh, it is doing the LU decomposition. It's doing partial pivoting, which means these row exchanges, but not any column exchanges. Yeah, oh, I guess, okay, so I guess the partial pivoting means you're not doing both rows and columns, but then in particular, we're doing the row interchanges. So in fact, this algorithm that we've just talked through in some detail is basically exactly what's happening when R or any other package calls LAPACK to do this, to do these sorts of calculations. Okay. So the next thing I wanted to do was walk through a different one of these decompositions called the Cholesky decomposition, just to give another example, and we're going to count for the Cholesky, we're going to take the time to basically count up the number of operations as an example of doing that. And on problem set 7, I'll ask you to count up the number of calculations involved in doing the LU calculation. Okay, so the difference between the LU and the Cholesky is with the Cholesky, we're assuming that our A matrix is positive definite, or at least positive semi-definite. Okay, so necessarily this means that A is going to be symmetric, And also that the diagonal elements are going to be positive because we're talking about positive definite is equivalent to a covariance matrix, so we're going to have positive variances, which are the values on the diagonal. Okay, so what is the Cholesky decomposition, and how do we go about finding the Cholesky decomposition? So the idea is that there's a mathematical result that says we can decompose a matrix A that's positive definite into an upper triangular matrix multiplied by the transpose of that upper triangular matrix. So the mathematical result sort of leads us into what the computation is to be able to find this. So we've got, let's see, how do I want to write this? So we know that we have U transpose U equals A, and so I've got A11, A12, A1n, A22, A2n. These guys exist, but I'm not going to bother writing them because it's a symmetric matrix, so it's just the flip of the values on the upper triangle. And so the idea is, okay, how would we go about finding what the elements of U are? So I know that U is going to look like this. And similarly, if I take the transpose of it, okay, so what do I need to do? And I'm going to see if I can manage the board well enough to have this all appear in reasonable places. Okay, so if you just sort of stare at this and know that there are zeros here, you may be able to get a sense of how we should start off this algorithm. And in fact, I've sort of already written out some of it up there. Which is, how would I get A1? Well, that's just going to be multiplying this column by that row, but everything in this row and this column are zeros except for the first element. So that means that A11 equals U11 squared, and therefore that U11 is the square root of A1. Okay. And I'm now going to work my way across the first row and figure out what the U12 and U13 is. So now what do I do? Well, I've got U12 times U11 plus nothing is A12. So U12 times U11 is A12. So now I've got a, sorry, I'm trying to find it, of course. So U12 equals A12 divided by U11. It's not going to be hard to see that I can generalize this to be U1j is A1j over U11. So that's going to, if I just redo this as a for loop, that's going to give me all of these. All of these values here. All right, so let's start to count up our operations here. We've got, we have one square root, and then we have n minus 1 divisions. And in the next steps, we're going to have some multiplications, so we'll just write it out explicitly here. We don't have any multiplications here. Okay, questions so far? Okay, so now it just basically gets a little bit more tedious and we have more bookkeeping, but it's just doing out the arithmetic. So if I now want to find U22, that's going to be U12 squared plus U22 squared equals A22. And therefore U22, which is the next one we're trying to find, is the square root of A22 minus U12 squared. And then we're going to have things that look like U12, U13, U22, U23 equals A23, and therefore U23 equals A23 minus U12, U13 divided by U22. And we're going to have a similar set of equations that look like this. How many of them are there going to be? There are going to be n minus 2 of these. So there are going to be n minus 2 equations that look like this. As I basically work my way across and try and find all of the values along this row. Okay, so let's go back to our counting. Again, I have one more square root. How many divisions do I have? N minus 2 divisions, because I have n minus 2 calculations that are like this, and those are the ones that involve division, so I have n minus 2 divisions. And how many multiplications do I have? N minus 1, right? So I've got n minus 2 from here, but then I've got a square up here that we need to remember. So I've got n minus 1 multiplications. Okay. And I can continue on in this vein. And if I did that,
should we be counting adds and subs?
yeah, so that's what I said last time, which is we're going to ignore the additions and the subtractions. Basically, two reasons. One is that they tend to be less expensive to do, and also that there usually is basically, whenever you do a multiplication or division, there's usually an addition or subtraction that goes along with it. So it's almost always just twice as many if you counted both of them as if you just counted the multiplications and divisions.
In terms of less expensive, with modern chips, aren't multiplying divides as fast as adds and subs?
You might know more about it than I do. My understanding is that multiplication division is more expensive, but I haven't looked into it in much detail or in the last few years. So, okay. So that was the first row. This is the second row. When we get down to the third row, what we'll find is there's one square root, and that there are 2 times n minus 2 multiplications, and that there are n minus 3 divisions. So, okay, so I'm not going to do sort of a formal proof and write this all out in great detail, but let's just sort of look at the pattern of what's developing here. We have one square root for every one of the rows. Right? So we should end up getting n square roots. And then what do we have for divisions? We have n minus 1 plus n minus 2 plus n minus 3 on down. So we're going to have n minus 1 plus n minus 2 on down to 1. And then for multiplications, if we look at it carefully, we realize it has this sort of form where we've got 1 times n minus 1, and then 2 times n minus 2, and then it would be 3 times n minus 3, and so on and so forth. So it's basically 1 times n minus 1 plus 2 times n minus 2 plus 3 times n minus 3. And if you sort of just keep going with that and just check things at the end of the day, what we'll realize is that we end up getting, this is the sum of I from 1 to n minus 1 of I, and this ends up being the sum from I equals 1 to n minus 1 of I times n minus I. Okay, so I've sort of skipped over details, but I think you can hopefully see where this is coming from. And if we took the time to write out the steps in a little bit more detail, it would makes sense that this is what we get. Okay, so now we basically just need to make sure we can add these things up, and then we're going to be able to figure out what's the order of the calculation, which we should find is an n-cubed calculation, again, just by the intuition that if we thought about what we're doing, we're basically doing 3 for loops. So again, this idea that the number of for loops, 3 nested loops, that the number of for loops corresponds to the order of the calculation. So I'm basically going to ignore the square roots. So they're presumably going to be more expensive than doing the additions and multiplications, because you have to go through some algorithm to find the square root. But there are only n of them, and these other calculations are going to be order of n cubed and n squared. So if we look at this guy, recall our formulas from last time, which is the sum from I equals 1 to n is of I is n times n plus 1 over 2. And the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Okay, so this one is going to give us, sorry, I'm sort of running out of space here, n minus 1 times n over 2. So that's from the divisions. And then we're going to have to do a little bit of arithmetic playing around here to get this in terms of expressing as a sum over I and sum over I squared. But once we play around with that in combined terms and do the arithmetic, that is going to work out to n cubed over 6 plus something that's order of n. So it turns out there are no n squared terms in this. They happen to cancel when you do all the arithmetic. Okay, so this, when we now look at it, if we've combined all these terms, we can see that what do we have? We have, this is n squared over 2, so this is n cubed over 6 plus n squared over 2 plus order of n. Let's see, so what do I want to say about that? Oh, well, let me pause. Any questions? Isn't it beautiful? Right, it's basically ugly bookkeeping and ugly arithmetic. That's sort of what it comes down to. And ugly like subscripting and having to write things out. Okay, so what do I want to say about this? It's order of n cubed, but in particular it's n cubed over 6. And if what you guys will show on problem set 7 is that to do the LU decomposition is, by comparison, is n cubed over 3 plus I forget what the other pieces are. But they're pieces that are either order of n squared or order of n. So this is the LU. This is the Cholesky. This is half as computationally expensive as that. They're both order n cubed, but this one is half as many computations. As n gets large, it's converting such that the ratio of these two is that the Cholesky is half as much as the LU decomposition. So if you do have a positive definite matrix, then you can solve a system of equations with that positive definite matrix more quickly by doing the Cholesky decomposition than you could by doing the LU decomposition, because it's only half as expensive to get to the upper triangular, to get to the triangular factor, and then you can do back solves and forward solves to get to solve the system of equations. So if you had, if you do have AX equals B, then either I can get to LU X equals B, and now this is going to be L inverse B, U inverse B. So here's a forward solve, and then the result of this is a vector, and here's a back solve. Each of those is going to be n squared over 2, so for that one, and then this one's going to be n squared over 2. Or, if A were positive definite, I still have AX equals B, I have U transpose U X equals B. So I have, oh, this was X equals. So now I have X equals U transpose inverse B, U inverse. Right, this is a lower triangular matrix, U transpose, so this is just a forward solve as well. This is also n squared over 2. And this is n squared over 2. So the back solves or the forward solves that are involved in the second step of all this are the same, regardless of whether I'm doing LU or the Cholesky. But the original factorization is half as expensive for the Cholesky as is for the LU decomposition. And that's the thing that's going to dominate if n is large, because those parts are n cubed and these parts are n squared. Okay, so one more question for you guys is, when I look at n cubed over 3 and n cubed over 6 and I say this is half as much, it sort of makes intuitive sense that it's half as much. Like, think about what I'm doing. For the LU, I'm computing L and U. For the Cholesky, I'm just computing U. I'm just computing half as many elements for the Cholesky decomposition. And that comes from the fact that the positive definite matrix is symmetric and has all this structure to it. So you can sort of think of it as, well, for LU, I'm getting a lower triangular matrix and an upper triangular matrix. For the Cholesky, I'm computing half as many elements to do it. And so it makes sense that it's half as computationally expensive. All right, questions or comments? Yeah, go on.
So when you like doing work, like how often do you use like decomposition?
I use them all the time. I mean, statisticians use them all the time. It sort of depends on exactly what kind of statistics you're doing as to which of the decompositions you use. So you might end up using, if you're doing principal components analysis, you use eigendecompositions all the time. If you're, like I do, working with spatial data, I use Cholesky decompositions all the time. If you're fitting a lot of regressions, then under the hood you're doing QR decompositions all the time. So it sort of depends on what kind of calculation, what kind of operations you're doing. But you may not know you're doing it when you use LM, but every time you use LM, there's a QR decomposition being done. Okay, so I said if I did want to solve a system of equations with a Cholesky decomposition, here's what I just wrote over there, and here's the R code that goes along with it if I wanted to do this in R. Here's another response to Guang's question, which is, suppose I said to you, I want to generate y such that y is multivariate normal 0 with covariance matrix A. And I say, okay, go do it. Right? You're like, well, what do I do? Right? So the standard algorithm for doing that, a little bit lost on the page here, is to take, let me make sure I get my, right. So to take U transpose times Z. So I've got U transpose U equals A. So A is a covariance matrix, it's positive definite, I can do a Cholesky decomposition. So that's this. I take U transpose times Z, where Z is normal 0, the identity matrix. So this Z is just a vector of n independent standard normals. If I do this, then y equals A U transpose Z. The covariance of y is U transpose covariance of Z, but the covariance of Z is just I, U, U transpose U, A. So that's just the proof that this works, and this is the standard way you generate a multivariate normal random vector. Okay. The other comment I'll make, maybe I'll switch over and just show this as a little demonstration. So we've already seen that the LU decomposition could run into trouble if I try and divide by something that's numerically very small. And in fact, if that were 0, the algorithm would stop unless you were doing the pivoting. So what I'm going to do here is this matrix is, I won't say why, this matrix is basically a, we've sort of seen examples like this before. This is basically the covariance matrix of a time series. by definition, mathematically, or not by definition, but you can prove that this matrix C is positive definite. Okay. But if we compute the eigendecomposition on a computer, and if I look at the last 5 eigenvalues of this matrix, what I see is actually that all 5 of them are negative. Okay. So the true mathematical eigenvalues of this matrix are all so close to 0 that the inaccuracy in doing the eigendecomposition is enough that they're not actually reported to be positive, they're not reported to be 0, they're actually reported to be negative, even though we know mathematically they're positive but small. So you can't actually, we could do a generalized inverse here, which would be the standard way of dealing with this if we were using the eigendecomposition. But that basically the same numerical inaccuracy messes us up if we try and do the Cholesky decomposition. It says, wait a minute. It says the leading minor of order 32 is not positive definite. So basically what it means is it was marching along. It was marching along, starting with the first row, marching along the second row. And when it got to the 32nd row, let's look at our algorithm here and think about what could go wrong here numerically if we're trying to do this calculation. Yeah, I'm taking all these square roots. So if I get to a point like this, where this is a number that just comes from wherever we're getting the A matrix from. It's represented with as much accuracy as we can represent it. This guy is the result of doing a computation. It's probably going to be represented with even less accuracy than the original elements of the matrix were. So if the true mathematical value difference here is very small, then we could get that numerically the inaccuracy is enough that this actually looks like it's bigger than this, even though mathematically we know that this is bigger than this. So you get a negative number here, it tries to take the square root of a negative number, it says, I don't know what to do, it stops, and this is the error message that you get. So maybe, hopefully not too surprisingly, we've already seen pivoting with the LU decomposition. There's a version of pivoting with the Cholesky decomposition that basically what it does is, if it gets to a point where it sees something like this is going to be negative, and so it tries to take the square root of a negative number, it does some pivoting, and it basically pushes all of those rows that cause those numerical problems. It basically pushes them down. And so you end up with a Cholesky decomposition. You can actually look at help on Cholesky and see that you can tell it to, so you see there is a pivot argument here. By default it's false, so it's going to give you back arrows like this if you have a numerically non-positive definite matrix. But you can tell it to use pivoting. And then what it will do, let's see if where did I sort of lost track of where I am here. Oh, here we go. So I can tell it to use pivoting. It gives me a warning, but it still completes. And what we should see, hopefully I'm right here, yeah, what we see, that's interesting. I thought it was basically going to put zeros down here in this lower part of the matrix. So I'm not totally sure what's going on here. What I was going to say is the general idea of the Cholesky, which doesn't seem to be quite borne out here. I'd have to look into why. The general idea of pivoting with the Cholesky is that you basically end up with your matrix U, and up to a point it's fine. So you've done some pivoting along the way, and you basically accumulate zeros down here in this part of the matrix. So the fact that it has ones on the diagonal down there I'm rather confused by that. Maybe I will try and figure that out afterwards. But I also want to sort of motivate what this is doing and why this is okay in some sense. So let's go back to my how do I generate a multivariate normal random variable and think about what I'm doing there. I'm taking U transpose, so I've got to transpose this guy. So I've now got a lower triangular matrix, and these zeros become zeros here. Right? And now let's think about what I do when I take my z vector and multiply it by these. And I'm going to go back to what we talked about with the eigendecomposition, this idea of taking random numbers, random weights, and multiplying them by feature vectors or pattern vectors. Same thing here. You can think of these vectors as the patterns, and these are random weights that are getting multiplied by the features of the patterns. So, okay, I've got z1 multiplied by the first column, z2 multiplied by the second one. At some point, whichever, it doesn't matter what these z's are down here because they're being multiplied by zeros there. So what is this saying? Well, it says for these guys down here are basically representing components of A that are linearly dependent. So it's basically redundancies in the matrix from a numerical perspective. And so the fact that I zero these guys out doesn't really matter that much because they're basically redundant. Redundant given the because of the redundancy, it doesn't matter that I'm not accounting for them when I compute my y. Another way of looking at this is basically that there's very little variation associated with those terms. Okay, so I think that's all I want to say about that. Any questions or comments? Okay, so the next decomposition we're going to talk about is the QR decomposition. So here we're starting to get into thinking about regression. So I think maybe I erased. No, I still got it up there. So basically, you can take any matrix A and decompose it into this QR decomposition. So Q is going to be, I've written it here, Q is going to be orthogonal, and R is going to be an upper triangular matrix. And there's sort of two variations of this. There's sort of the standard QR, and there's what's called the skinny QR. Okay, so I have some matrix X. Often we're going to have n bigger than m. I'm going to call this P here because usually we're thinking about a regression design matrix, a matrix of predictors or covariates, and usually often people use P to mean the number of predictors. So we can decompose that into a Q matrix that is n by n, and an R matrix that is n by P. But if you do this, what you'll see is that this is upper triangular. And then there are zeros here, and this whole block down here is going to be zeros. And so the implication of that is even though you can compute these vectors such that this resulting Q matrix is orthogonal, they're sort of immaterial from the perspective of using these pieces, because when I multiply by R, this zero block just zeroes out all of this part of the matrix. So the skinny QR basically is you do the QR and you just return back this part of the Q matrix, and you just return back this upper triangular R matrix. So then you would have the Q being n by P, and you'd have the R being P by P instead of the dimensions that I showed there. Okay, so one of the reasons this is particularly useful for regression is as follows. Let's see. So I've got X transpose X. Suppose I decompose X by the QR decomposition. So this is now going to be QR and QR transpose, which if I then flip the R and the Q by the usual rules of dealing with transposes, I've got R transpose Q transpose QR. Okay, so why does this equality hold? What do we know about Q? Q is orthogonal, so the transpose of Q is the inverse of Q. So this is just the identity matrix, so I just get R transpose R. This was n by p, so this was p by p as usual. This is also going to be a p by p matrix. But if I think about, do I have it down here somewhere? Yeah. If I think about running a regression, here's X transpose X, here's R transpose Q transpose QR, here's X transpose written out in terms of the QR decomposition. These disappear. R is invertible. So if I multiply by R transpose inverse here and I multiply by R transpose inverse here, I have that I can write my regression, my normal equations for solving the least squares estimators. I can write them as R beta equals Q transpose Y. I don't have to do any of this computationally, I just can work that out mathematically. And now I have this nice set of equations. What's so nice about this? This is already upper triangular. Remember all of that, all of the motivation last time of, I said, what if we had an upper triangular matrix, then we can solve this system of equations really easily. Well, the QR decomposition gives us this set of system of equations where I have an upper triangular matrix. So this is just a back solve then to then do this computation. Let's see. So I guess I'll quit there. Next time we'll talk. I'll give you sort of a bit of a flavor of a few different ways of computing the QR decomposition, and then I'm forgetting what else I'll talk about. But I'll start off with that.